and we can find a linearization in 3 dimensions, the form of that would be W equals f of a, b, c, right? So if we assume we're working around the point x equals a, y equals b, z equals c. Right, so we have the x partial evaluated at ABC times x minus a, plus the y partial at ABC multiplied by y minus b, plus the z partial evaluated at ABC times z minus c. Okay, so that structure, hopefully that pattern is clear. This right-hand side is now the linearization. About the point ABC. All right, so there's the basic idea. It's a generalization of what we know about the tangent line approximation. And there's a few things that are built on this. So first, we say a function is differentiable. And we're going to go back to a function of x and y here. We say it's differentiable at AB if the tangent plane approximation, or the tangent plane is a good approximation. Or x, y sufficiently close. Whatever that means. All right, and what are we talking about? Well, the way your book expresses it is that delta z equals f of x, y minus f of a, b. And we want to say that this part of the linearization, right? Notice we're just pulling the constant off from the front of the linearization. Now the function is not necessarily exactly the same as the linearization, so this equality is not going to hold unless f is itself a linear function. What's left over here so we have an epsilon 1 delta x and an epsilon 2 delta y. Delta x is equal to the x minus a. Delta y is equal to the y minus b. And we have to, so this is the error term between the function and its tangent plane approximation. And what we want is that epsilon 1 and epsilon 2 both go to 0. As delta x and delta y go to 0. right? So in other words, the approximation does a good job in the sense that the difference between the approximation and the actual function is small, close to the point about which we're approximating. And that small error, in fact, does go to 0 as we approach the point. All right, so that's a very reasonable seeming way of saying whether your approximation is good or not. It's not so clear from the statement here how you would actually prove that a function is differentiable, right? Based on the statement, you would have to find the linearization and look at this extra bit, this difference between the linearization and the function, and somehow prove that that goes to 0 as it's supposed to. Doing that directly is not necessarily going to be an easy thing, but that's not something we're going to really worry about in Math 243. There's a result that makes your life a little bit easier, right? So this is a useful result. There's a theorem that says if the partial derivatives fx and fy exist near the point AB and are continuous at AB, then the function is differentiable at AB. Okay, so why is this useful? It's useful because computing partial derivatives is something that we can do in a straightforward, pretty mechanical way. Right? It's not hard to compute partial derivatives in general. We have to check whether these things exist and whether they're continuous at our point. But essentially, if we can compute a tangent plane approximation and these partial derivatives, right, they have to exist in order to be continuous. So if we can compute them, if they're continuous at the point, then our tangent plane approximation is good. Our function is differentiable. All right, so let me just pause for a second and ask if there are any questions so far. All right, so I'm going to assume you're in good shape. Please ask questions if you've got them. So there's another way of thinking about linearization and tangent plane approximation, and that's in terms of differentials. So the underlying ideas are the same here. The way you should think about this is it's a different way, slightly different point of view. Okay, there's a little bit of notation and terminology that you have to remember, but really what you're doing is just talking about linearization in slightly different language. Okay, the ideas are the same. So dx dy are differentials. And we can think of these as independent variables. And we can look at dz as the differential dz as fx of ab dx plus fy of ab dy. Sometimes this is written as dz by dx. Remember, we're talking about the surface z equals f of x and y. So we're making the correspondence between the z and the function f of x and y. All right, so this equation that we just wrote down, effectively, we can think of, sorry, fudge, I wrote the wrong thing here. All right, so notice you don't have a, b there, so I slipped and wrote a and b. These should be functions of x and y. So we can think of this as a skeleton of sorts. A skeleton or a template for producing the tangent planes. Right, if we restrict to a particular point, x equals a, y equals b, and evaluate this right-hand side, we get the linearization of our function at that particular point. Okay, so there's a little bit more notation. Right, so we have a dx, we also have a delta x, we have a dy, we also have a delta y, we have a differential dz, we also have a delta z. So these are related. They're not necessarily the exact same thing. So it's difficult for me to draw in 3 dimensions, but let me just try to do this, the analog for what we're talking about in terms of the tangent line. So if we have our function, we've got our tangent line to the function. So let's say that this actually comes together. Right, so this would be y equals L of x. So what we can do is we can think about this dx is just going to be the difference from our working x value to our base point x equals a. Okay, those are just identified with each other. In this context, we're going to make a distinction between dy and delta y. So the differential dy that's the difference in the y values between our base point and the point on our tangent line approximation or on our linear approximation corresponding to moving delta x in x along there. The true delta y is the true difference in the y values between the function at that new x value and our base x value. So linearization essentially, if we say that the linearization is a good approximation, what that means in this context is that delta y is well approximated by dy as long as we're close to our base point. In other words, trying to evaluate your function by just evaluating on the tangent plane does a good job. All right, on the tangent line in this case does a good job. And when you go up to a function of two variables, delta x is going to be the same as dx, delta y is dy. Those two are going to be identified, and now delta z is going to be the true difference between evaluating your function away from your base point and at your base point. dz is the difference by moving along the tangent plane. All right, so why do we bother with this? Well, in many applications, the language that is favored is to think in terms of differentials rather than think in terms of linear approximation or tangent planes, even though the underlying idea is exactly the same. It's exactly the same thing that's going on. So you should be familiar with the notation. All right, so if this is not familiar, you can go back to section 3.10, I believe it is. Let me just make sure I remember that correctly. All right. So that's linearization and tangent line approximation. Right, so if you review that material, it might make the tangent plane approximation a little bit easier to digest. All right, so let's actually try to do some things. All right, so we have 14.4. Let's look at number 1 here. We've got the surface z equals 2x squared plus y squared minus 5y. We're going to look at the point 1, 2, negative 4. And the directions say to find an equation for the tangent plane to the given surface at the specified point. All right, so what do we need? We need to remember our basic formula. All right, and so here we have z equals some function of x and y. That's our function of x and y. So df dx partial of f with respect to x, that's going to be 4x. And that's it. Partial of f with respect to y is going to be 2y minus 5. Here, a is equal to 1, b is equal to 2. So make that cursive. And f of ab, therefore, is equal to -4. That's the z value corresponding to the given x and y values. And let's just check there. If I plug in x equals 1, the first term, 2x squared, goes to 2. Y squared is 2 squared, that would be 4. So 2 plus 4, sorry, y is 2. 2 plus 4 is 6. And then we want to subtract 5y, so subtract 10. So 2 plus 4 is 6, minus 10 is -4. That point really does lie on our surface. So if we plug in everything, a is 1, fy was, oh, sorry. Going too fast here. So fx of 1, 2, right? A is 1, so that would be 4. And fy of AB would be fy of 1, 2. So that would be 2 times 2 minus 5, or 4 minus 5 is -1. All right, so fx of AB becomes 4, x minus a, well, a is 1, so I have x minus 1. Fy of AB becomes -1. So we have -y minus 2. So that's our equation of the tangent plane. The z equals -4 plus 4 times x minus 1 minus y minus 2. In our linearization, is just the right-hand side of this equation. All right, so is everyone following along okay? Are there any questions on this calculation? All right, so I'm going to assume you're in good shape. So let me ask you all a question. Is this function z equals 2x squared plus y squared minus 5y, is it differentiable at this particular point where x equals 1, y equals 2? Yes or no? You have a 50% chance of guessing correctly. So I have yes. So what is the reasoning for that, Cameron? How do you know the function's differentiable? Exactly. So Cameron is using the chat here. So we have our partial derivatives here. These happen to be polynomials in x and y, so those certainly exist everywhere. They're continuous everywhere. So in fact, this function z is differentiable everywhere. Any place where I would want to try to approximate it, I can use a tangent plane approximation about that point. All right, so next. Let's just do another calculation here. So we have z equals e to the x minus y, and we're going to look at the point 2, 2, 1. All right, so we have the graph of the function e to the x minus y. So we know we're going to need the x and y partials of that. So x partial, we treat y like as a constant. We just get e to the x minus y. The y partial, we treat x like it's a constant. We get negative e to the x minus y. F of 2, 2 is equal to e to the 0, which is 1. Fx of 2, 2 is equal to e to the 0, which is 1. F sub y of 2, 2 is equal to negative e to the 0, which is negative 1. So tangent plane looks like z equals 1 plus 1 times x minus 2 plus 1 times, negative 1 times y minus 2. So we could just write z is equal to 1 plus x minus 2 minus y minus 2. And the linearization would be just the right-hand side here. Okay, and again, the exponential function is, in fact, continuous everywhere. All of its derivatives are continuous everywhere. So the function is differentiable everywhere. Any place you want to use as your base value, you can build a tangent plane around that point, and that will do a good job approximating the function as long as you're not too far away from the point. All right, so I just want to give a little bit of a warning. So let me ask you all. I believe there's quite a number of mechanical engineers in the class. So how many people have taken Math 353 at this point? Has anyone taken that, or? All right, so people are taking 351 now. So 353 is part of this 351, 2, 3 sequence. You're learning about differential equations in linear algebra in 351. You'll learn some more about differential equations and maybe partial differential equations in 352. And you'll learn some numerical ideas in 353. Finding linear approximations is something that is often very useful numerically. So that's something you might see in 353. So the question is, we've talked about differentiability, whether there is a tangent line approximation. It's a separate question whether for a given function and a given tangent plane approximation or tangent line approximation, given function and a given linear approximation, does the linear approximation actually do a good job under specified conditions? So it's going to be easier for me to draw this in 2D. So that's that's what I'm going to do here. So we have our function y equals f of x. We've got our linearization about this point. And you can imagine that if you're interested in function values in this little window around x equals a, that tangent line approximation probably is a reasonably good approximation. It's close to the value of the function. But if you go too far away, might not be a good approximation, right? Just because the tangent line approximation works well close to the point doesn't mean that you can use it indefinitely far away, arbitrarily far away. So you really have to be careful about that. This is not something that we're really going to spend time on in 243, but there are ways of sort of gauging not just whether a function is differentiable, but when is a given linear approximation going to actually be a good idea to use? When is it actually accurate? So that's something you should always keep in mind when you're doing this sort of thing. All right, so that's just the warning, the limitations. So if you look at the exercises at the end of the section, there's a bunch of pretty straight calculational type things at the beginning, where you're just computing the tangent line or the linear approximation. Then you have some word problems. Okay, so make sure that you know the basic terminology, you know the equation for the tangent line, and then it's important to actually be able to use these ideas. So you really need to practice with the word problems. So you have to sort of extract what's the function, what's the point around which you're evaluating, what's appropriate to do for the actual word problem that you have in front of you. Time is limited here, so you just want to do one more calculational thing. If you're asked to compute the differential of a function, okay, so that shows up in exercises 25 through 30. So we have z equals f of x, y. This is the function. F of x, y is the function. dz would be the differential, or df. Sometimes you use the notation df. So what's it going to be? Well, that's just fx of xy dx plus fy of xy dy. So remember, this is sort of a skeleton, or it's a pattern that you can use to build your tangent plane or your linear approximation wherever. All right, so that's how you put it together. So if you can compute the partials that you need, you can fill into this formula and get the differential. If you have the differential, you can evaluate at a given value of x and y to get the linear approximation about that point. All right, so that's where I think I want to stop for today. Are there any questions before we pack it up here?